Hi there, in this video we're going to look at time and frequency scaling. Now we'll start off with the time scaling. If we think about a sum function of time, and if we find the Fourier transform of it, we'll get some function of frequency f of j omega. Okay, so that's us taking the Fourier transform. Now if we were to then take that function of time and were to scale that time axis, so that's the time is getting scaled by some factor a. Now let's say a is a real number, okay, so it can be both positive and negative. The question is, what happens when we find the Fourier transform of this scaled function? Okay, what happens here? And that's a question that we're going to answer. So the first thing to do is to think about what do we mean by scaling an axis. So we note that scaling by a positive number and a negative number do two different things. Okay, so let's say our a is greater than 0. Then we've already seen that if we have, for example, a square wave here, so let's say that's 1, that's minus 1, the height is 1, that's time, and that's a function of time. Then if we were to say scale the t-axis in this instance here by 2, okay, so we've now got a function f of 2t, then what we could do is we could say, well, let's go to a point 1. Okay, so in this function here, when we get to point 1, we'll say what's the height of the function? Well, the height of the function is going to be 1 times the 2, which is 2 here, right? And so it's the f of 2, which is 0. So that height there is going to be 0. So let's go to a point, say a half. So when we get to a half here, we say what's the function here? The height of the function here at a half. Well, at a half, this up here is going to be 2 times a half, which is 1. The height of it is going to be 1, so that's going to be height 1. Okay, but anything outside above a half, okay, is not going to be within this function range, because if we get to beyond a half, we multiply it by 2, it's outside this function range here, okay, so it just gives a value of 0. So we just get a function that looks like that, okay. So it's got the same height, but it looks like it's squeezed in the t-axis, so that point becomes a half, that point becomes minus a half. Okay, so it may seem counterintuitive, but that's what it's doing. When we multiply by 2, we squeeze the t-axis. Okay, we squeeze the function. Okay, so let's then look at an example, f of half t. Okay, so in this instance here, if we went to say a point 1, we said what's the value of the function, so we go to a point 1 here, multiply it by a half, the value is 1. Okay, so the height of that there is 1. So let's go to a point 2, so we get to a point 2 here, and we want to know the value of the function. So the point 2 here, we go up here, and we take this function here, and we multiply our value here 2 by a half. 2 times a half gives us 1, the height of that is a 1. Okay, so when we get to this point 2, it goes up there to a 1. But when we go beyond this, okay, so we went to say 4, then we would have 4 divided by 2, which is outside this range here, so we wouldn't have anything. Okay, so it means that this function, it goes up to a value of 1 at point 2, and it's the same in the negative side as well. Okay, so you get a minus 2 here. So it has an effect when we multiply the axis by a half, we in effect stretch the function out. Okay, so that's what we're doing there when a is greater than 0. But when we have a less than 0, then well, what you can do is you can think about our function f of t. If we had a function f of t, then we could stretch that function, so we could change that function, and let's say a is minus 1, so then you would have f of minus 1 times t, which is just be f of minus t. Okay, so when we take a function and we produce the f of minus t of the function, that is in effect, it's just like taking the function and flipping it on the y-axis. Okay, so we had a function here say that looked like that there. When we multiply that by f of minus t, okay, then the function looks like that, okay. It's flipped in that axis, okay. And of course, if it's minus 5, then it'll be flipped in that axis and compressed, okay. And if it's say minus a half, it'll be flipped in that axis and it will be stretched, okay. So you can see these two processes are slightly different, okay. This one has an extra factor in it, so we have to look at them separately when we look to see what the Fourier transform is going to be. So let's go through and we're going to look at the first of all the Fourier transform of our function a of t, so when a is greater than 0. So let's say we're looking at a greater than 0, okay. Then we have the integral from minus infinity to infinity of some function f of at e to the minus j omega t by dt. Okay, now what we're going to do is we're going to change the variable, so we're going to let our x equal at. Now what's important is you understand why you do that. So what we want to do is we go up to this axis here, we've got a t-axis, and now we've got a different axis, okay, so that's a scaled axis there, okay, it's a 2t axis, so we'll give that 2t axis a different name, okay, we'll call it x, okay. And the reason for doing that is now we can say that's an x-axis, that's a t-axis, and we know the relationship between the two axes, so then we can find out what the difference is between these two axes in the frequency domain, okay. So that's the reason for doing that change of variable. But we know that if we're changing the variable here, then we must be changing it for all values of t, okay. So we then need to find out, well, what is t? Well, t in that instance then would have to equal our x upon a, and we're also interested in what dt is. Well, dt is just going to be equal to dx, because x is an independent variable, so it's going to be dx, and a is just a constant, so that will just remain there as a. So we need to put these into this equation and see how it changes that equation. So we're then going to have the integral from minus infinity plus infinity of our function. Well, our function now is at is now x, and it's going to be e to the minus j. Now again, we've still got our omega, but our t is going to be replaced by x upon a, okay. So we're going to have omega upon a, and we'll bracket that off, and we'll take out our independent variable x, so that's just omega x upon a, so we just replace the t by x upon a, and dt is just going to be our dx upon a, okay. So let's then rewrite that. If we were to, we can take the 1 upon a out, so we end up with our 1 upon a, and it's the integral from minus infinity to infinity of our function f of x e to the minus j omega upon a x times dx, okay. So that's for a greater than 0. Now for a value a less than 0, as we said, what we're doing is we're flipping this signal, which is equivalent to mapping it over or reflecting it in that axis. So in effect, if that was our plus infinity there, say plus infinity and minus infinity, then that would become minus infinity, and that would say it becomes a plus infinity, okay. So that's how those are related. So we're going to end up with, for a less than 0, we're going to have a function that would be an integral from plus infinity to minus infinity, so the limits of integration have been swapped. Still going to be f of x, still going to be e to the minus j, and it's still going to be omega a x by dx. Now, and is still going to be a 1 upon a. Okay, now another thing you have to note is that whenever you swap that axis there, the limits of integration, then if we had a function, let's say for example, I'll just go through the example so you can pick up. If we had a function, say from integral from 0 to 3 of some function f, okay, then that's equivalent to the minus of the integral of the function from 3 to 0 of f, okay. So it means that we're going to have a negative sign in here because of we've swapped over the limits of integration. Now, I suppose I could go through a wee kind of thing. You can see that there, okay. I'll draw it out and then I'll just kind of rub it off, okay, because it doesn't really, it's not really what I want to talk about. If we had a function there, so there's a function f, and we had a points 0, 1, 2 and 3, okay, then we could kind of think it loosely. We could think about an area here, we could think of an area here and an area here, and we could kind of say the area under that is going to be approximately, it's going to be say f of 1 times 1 minus 0 plus f of 2 times 2 minus 1 plus f of 3 times 3 minus 2. Now that's exactly the same as saying f of 3 times 2 minus 3 plus f of 2 times 1 minus 2 times plus f of 1 times 0 minus 1, okay. But the only difference being in this here is that these terms here are going to be negative, okay. So to make up for the fact that we've made these terms negative, we'd have to stick an extra negative term in here, okay. So that's where this negative term here comes in, and it's where this negative term here comes in, okay. So that's all we're going to do in there. So I'll just going to do this bit here, okay. So in the end, these things are equivalent whenever we stick in that negative term. So when we stick in that negative term, it means that we could rewrite this equation here, okay, that would incorporate this equation as well if we just incorporate this negative sign. So the way we incorporate the negative sign is to create the modulus. So then we're able to say finally that what we're going to have is 1 upon the modulus of a, the integral from minus infinity to plus infinity of our function f of x e to the minus j omega upon a x by dx, okay. And we can then say what's the difference between this and our actual Fourier transform we had for our f of t. So f of t, it would be f of t e to the minus j omega t by dt, okay, from infinity to minus infinity, okay. And now the only difference there is we've got this extra term 1 upon a, so you can then say f of at, and when you find a Fourier transform of it, you're going to get, well, it's going to be 1 upon the modulus of a, okay, times, now it's no longer the Fourier transform of omega, because now we've got a factor of a in, so it's now going to be j omega upon a, okay. So that there's a little Fourier transform, and that term there, oh, that term there, 1 upon mod a f of j omega upon a, that there is our question mark, okay. So that's us found out how this f of j omega changes. It changes in that manner there, okay. So it means that the magnitude decreases by the factor of a, okay, whether a is positive or negative. So if it's minus 3, it'll change by minus 1 upon 3, and if it's plus 3, it'll change by 1 upon 3, okay. And the same with the frequency term there as well, okay. So now Best to see it in a little example. If we now we've seen these examples, I've just done these examples, so but I'll put in the actual equations for them. So if I had our function there, and that's our function of time, that's our f of t, then what happens is the Fourier transform of that is tau upon tau, times sine a half omega tau upon a half omega tau, and it looks like that there. So we have a first crossover point there at 2 pi upon tau, and the height of that there is tau. Now whenever we look at f of 2t, f of 2t has effect of squeezing the axis like that there, okay. Now this is f of 2t, and by using our new equation there, then we can say that our value of tau was no longer tau, it's 1 upon the modulus a, so it's 1 upon 2, so we're going to have 1 upon 2 tau, and it's now going to be sine. Now it's no longer going to be our omega, it's going to be our omega upon 2, so you're going to end up with omega tau upon, now it would be 2 times 2, which would be 4, all upon omega tau upon 4, and again that would come away like this, and it would be equivalent to stretching this thing here in the frequency domain, and it would decrease the height there, so the height there is now a half tau, and this point here is 4 pi upon tau. And finally, if we were to look at f of a half t, would be equivalent to stretching it here, and this is going to be f of a half t, okay, and that's going to be, well, it's going to be a half upon a half, which is going to end up as 2, okay, so we're going to end up our value 2 tau, and it would be our sine omega tau upon our omega tau, and we would end up with a function that is squeezed in that domain, okay, and the height would be twice as much, so it would be 2 tau, but the cutover point there, the first crossover, would be pi upon tau, okay, so it's just half of that there, okay. So that there really goes through over the time scaling. Now frequency scaling, because of the symmetry of the Fourier transform, frequency scaling works exactly the same, okay. So we'd have 1, say, modulus of b, and if we have frequency, the frequency would be at t upon b, okay. So that there would be the inverse transform of some Fourier, some function j of b omega, okay. So just to be clear on this, what you have is a function of j omega, and it's been modulated by, it's been scaled by a factor of b, okay. So in the time domain it's equivalent to being the amplitude decreases by modulus of b, and the time is changed by a factor of 1 upon b as well, okay. So that's all there is for this, and the next video will go on and we'll look at some other property, okay. Thank you for listening, goodbye.